Hi, everyone. Today we're going to do the pH curve of weak base and strong acid titration. Now, the problem is we are titrating 0.1 molar ammonia, 20 milliliter with 0.1 molar strong acid HCl. First, we have to calculate the volume of HCl to reach the equivalence point. Writing the net ionic equation, H plus with ammonia to form ammonium ion. Using MAVA is equal to MBVB for our calculations. And since we have 0.1 molar, 20 mil of the weak base, and we can calculate the volume of the HCl to be added. Actually, it should be VA, not VB. VA is 20 milliliter of the strong acid. Now at point A, when no HCl is added, you only have the ammonia in the flask, which ionizes partially in water to form hydroxide and ammonium ions. So we use Kb to solve the problem. 1.8 times 10 to the minus 5 equal to x squared over 0.1 minus x. Solving for such hydroxide ion is 1.3 times 10 to the minus 3 molar. pOH is 2.89. The pH subtracting pOH from 14 is 11.11. Now, initially, the pH is high. This is because we only have the ammonia in the beaker or in the flask, and it ionizes partially to form hydroxide ion, which is basic. Now, at halfway to the equivalence point, after we added 10 milliliter of the strong acid, so we have 2 millimole of ammonia in the flask. We have now 1 millimole of hydrochloric acid delivered from the burette. So writing the net ionic equation using the ice table for our setup, we find out that all that hydrochloric acid is used up, but we have 1 millimole each left of the ammonia and the ammonium. This is clearly a buffer solution, and that we can use the Henderson-Hasselbalch equation to solve it. Calculating the concentration of the two components, it is 1 millimole over 30 milliliter, which is 0.033 molarity. And substitute the numbers into the Henderson-Hasselbalch equation. We have pH equal to negative log of Ka. So pH is 9.25. At halfway to the equivalence point, pH is equal to pKa because ammonia and ammonium concentration are the same. Now, at point C at the equivalence point, after 20 milliliter of HCl has been added, now we have 2 millimole of ammonia and 2 millimoles of hydrochloric acid delivered from the burette. Writing the net ionic equation, setting up the ice table, we find that both the strong acid and the weak base are consumed. Now we have the ammonium salt, which is 2 millimole, and has a concentration of 0.05 molar because it's 2 millimole over 40 milliliter in the mixture. Now this ammonium ion would hydrolyze in water to form ammonia and hydronium ion. Therefore, this is at equilibrium, and we can use Ka value, which is 5.6 times 10 to the minus 10, to calculate the X value. The X is the hydronium ion, which is 5.3 times 10 to the negative 6 molar, and pH therefore is 5.28. Notice that now with the weak base strong acid titration, pH is below 7, more in the acidic region. Beyond the equivalence point, let's say we added 30 milliliter of HCl, so HCl is added in excess. In the flask, we still have 2 millimole of ammonia, but now we have 3 millimoles of hydrochloric acid. Writing the net ionic equation, setting up the ice table, we find that we now have 1 millimole of the hydrochloric acid left while we created 2 millimole of the ammonium ion. But the ammonium ion does not contribute significant pH to the solution as the hydrochloric acid would. Therefore, the pH is dictated by the remaining hydrochloric acid, which is 1 millimole over 50 milliliter of volume in the mixture, which is equal to 0.02 molar. Now the pH, taking negative log of the 0.02, is 1.70. And the pH is determined by the excess hydrochloric acid remaining, or the hydrogen ion remaining. Let's take a look at the pH curve. So we start with high pH, 11.11, because we only have the weak base ammonia ionizing partially in the flask, point A. Now we go to point B, which is halfway to the equivalence point, where ammonia and ammonium ion concentration are exactly equal, so pH of 9.25 is equal to pKa. Now we gradually go down to point C. At the equivalence point, pH is due to the hydrolysis of the ammonium ion salt, and pH is 5.28 in the acidic region. Beyond that would be point D after hydrochloric acid is added in excess. And notice the buffer region between point A to point C. When going from point A to point B, ammonia is in greater concentration than ammonium. When going from point B to point C, ammonia is in greater concentration than ammonium. So summarizing the characteristic of the pH curve, again, once beginning pH is high, because it's basic, due to ionization of NH3 in the flask. The buffer region goes from point A to point C, where you see the shoulder, because of the presence of ammonia and ammonium ions. The decrease in the pH is more gradual near the equivalence point. The slope is less steep. From A to B, ammonia is in greater amount than ammonium. At B, halfway to the equivalence point, ammonia and ammonium are equal. pH is pKa 9.25. From point B to point C, ammonia is lesser amount than ammonium. Now at the equivalence point, the weak base and strong acid have been consumed, and the hydrolysis of ammonium produces a pH of 5.28. And at point D, beyond the equivalence, pH is 1.7 based on excess hydrogen ion present. We can make use of such a curve to determine two things again. One, the volume of the acid added at the equivalence point to find the molarity of the unknown weak base using MAVA is equal to MBVB. So you notice the volume of HCl is 20 milliliter, and we know the molarity of HCl 0.1 molar, so we can calculate the molarity of the weak base ammonia using this equation. We can also estimate the Ka value of the weak base ammonia from the curve at halfway to the equivalence point, which is about between 9 to 10. And at that point, pH is equal to pKa. Furthermore, we can then use Kw divided by Ka to find the Kb value of the weak base. Summarizing the pH calculations. One, we calculate initial pH based on ionization of the weak base, set up the ice table, use Kb and concentration of the weak base to find hydroxide ion concentration. Between the initial pH and the equivalence point, solution becomes a buffer. We use stoichiometry to calculate amounts of each buffer component, then use the Henderson-Hasselbalch equation to calculate the pH. At halfway to the equivalence point, the buffer components are equal, pH is equal to pKa. And at the equivalence point, pH is based on the hydrolysis of the salt form, use Ka to find hydronium ion. Beyond equivalence point, pH is determined by the excess hydrogen ion present. Summarizing what we have learned in this video today, we learned how to calculate the various pH values of a weak base strong acid titration. We also learned the characteristics of the pH curve at the various points. And we further analyzed the pH curve so that we can determine the molarity of the weak base and the Kb value from it. I hope that you have found this video to be helpful. If you like it, please give us a like and subscribe to our channel. And I hope to see you again real soon.